All right. Any questions before we start? So what did you do last time? Can somebody tell me quickly?
Augmenting Convex functions.
Yes. Something more?
Yeah,
For Convex function, extra local movement gradient of x extra times x minus x square and greater than 2.
Yeah, that's a necessary and sufficient condition.
sufficient to let this Convex.
Yes. What else? Anything more? Sorry?
Uniqueness of global minimum.
Mhm. Yes. And local is global. And then we finally looked at the projection theorem. Okay, so now let's look at application of the projection theorem. Hopefully people remember what projection theorem was. So let's suppose you want to solve the following problem. Okay. Subject to Ax equal to. So C is some given vector and I want to minimize and find x such that Ax is equal to 0. Okay. How can I use my projection theorem to find a solution to this?
Restriction in the subspace.
Yes, very good. So observation 1, Ax equal to 0 is a subspace. All right. So what should happen? Because of the part D of the theorem, the optimal answer has to be something, something. So C is somewhere here. This is my space, let's say. What has to happen? That this is somehow perpendicular to it, right? So X star is perpendicular to what? Yeah. So sorry.
Perpendicular to x minus extra.
Yes. So what is the answer I can write essentially?
So c minus extra times x minus extra is c.
So C minus X star whole transpose X is equal to 0. That much I know. But still the problem is to find X star. How do I find an X star? You can guess and prove if you want. Because all I need is this is necessary and sufficient. All I have to produce an X star such that this is satisfied and Ax star is equal to 0. I am done. You've seen this in many different ways. You've seen something called a pseudo inverse of A. You never heard of it, that's okay.
But like you need how to apply pseudo inverse. You need to like somehow. So we have like c minus x transpose x star transpose times a.
It's all symmetry. That's all you have to somehow make sure that something happens and all it ends up becoming 0. So something should click, right? That I is an identity matrix, something minus something times something should be that correct vector. That much should pop up in your mind. They want to produce something, this transpose X is equal to 0. So what is happening? That this vector essentially is lying perpendicular to X for every X. So what kind of vectors have you seen? So let me give a guess. Let's see if it works. So wherever I write I is an identity matrix. So this you have seen before. It's called a pseudo inverse of A. If A itself is not invertible, this is invertible. Now, can you construct something in? So there is something missing here and something missing here. Can you just guess what that should be? Sorry?
Yes, what is perfect. It's fine.
Everything is written on the board. Symmetry doesn't help you.
And
Something has to cancel off, right? So
eight and
Yeah.
okay, so suppose this is my guess. How would I verify the guess to be correct? See, it's important. What you're saying is because of that projection theorem. Otherwise, I'll have to redo, or possibly many other ways. I have to find this out. Now, can you go and check that this is true as well as AX star is equal to 0? As long as both these conditions are satisfied, that X star is in fact the right X star. Is everybody following this? What's going on? This is guess and prove, but because of the sufficiency condition, that's okay. It's not actually difficult to guess. Then, sorry, how does it pop out? If you want, you can do it that way. But now, can somebody verify quickly it's true or not? Or am I making a mistake? See, all you wanted was somehow this to have, this to have something, some term, and eventually an A, so that A times X becomes 0. That's all you really wanted. This exactly gives you that. So this will become C transpose I, which will cancel off with that C. What is this? C minus X star, right? So C minus all of this. I minus A transpose A inverse A C whole transpose multiplied with X, which remains outside. And this C cancels out. And you take a transpose. So what do you get? C transpose. This guy is symmetric, so it doesn't hurt. Then A transpose and A times X. And because A times X is 0, X belongs to the subspace already. So this is 0. So this definitely satisfies this condition. Now, all you have to check is whether AX star is 0 or not. That also is a requirement because it better belong to the subspace. And that is again easy to check.
and then AC minus A transpose.
Sorry?
Get AC minus A transpose.
Yeah,
Transpose here.
that will cancel off.
But
Maybe I've written it wrong.
A actually
Yeah, A transpose. So that matches. Then essentially, if you write this way, then you have to just adjust for that. So thanks for making this correction. So this is the power of the theorem, essentially. Okay, so we're going to take this as a primitive. We're going to solve a very generic quadratic problem, which will keep showing up. So that's like the canonical example of a convex problem. What is the problem? Let's minimize half just for the sake of when you take the derivatives, you'll end up getting no terms in the front. Q bar plus C transpose such that. This is one of the most canonical examples of a convex problem. So now, using the last result, can you give me an answer for this? Keep in mind what we did. We solved that problem. So all you have to do is to write this problem in terms of that problem. See, this is half the battle won in this course. If you can write one problem and express it as a problem for which you can solve it. And that's where like the theorists in convex optimization essentially end up doing that in a very beautiful way. And generally is a non-trivial problem to see that one problem is equivalent to another problem. Here it is easy.
What is this bar?
Some given vector.
This is how that,
Q is also a positive semi-definite matrix or positive definite, for example.
if you somehow try and transform this into x minus q on modulus of x minus a.
Such that Ax is equal to 0. That's also important. Because that's the solution I know. So why I'm doing the exercise is that this is very meaningful as we go forward to write one problem as a function of the other problem. And you can assume x bar to satisfy Ax bar is equal to b. So let me write it. Q is positive definite. X bar is a vector such that Ax bar. Yeah. You're saying something?
Not quadratic or linear problem.
So
So
not allowed.
not like that. Like you can show it has some square term
Fine.
plus some constant.
Do it.
Constant.
The Q is being given for you to be positive definite. So automatically something is for free. You can take square roots. Sorry?
No, that makes it easier than Q.
That's very important. If Q is even positive semi-definite is okay. So somehow you have to write, so like think of a new variable y, which is some function of x, q, yeah, q and x bar. Where in y space, you can express this problem as a minimization of something minus something whole square. That's the point. And you also want ay equal to 0. Where a can also be transformed. See the problem here, the A is generic A, right? I can replace some other matrix here as well. So when I'm starting here as Ax equal to B, I'm allowed to write it is equal to some D times Y equal to 0. That is in the same form as before. Some
Q to be some H transpose H level.
just take Q to the power half. What's wrong? If you like to write it just like it, you can write Q as Q power half times Q power half. No, nothing wrong with that. You're allowed to do that because Q is PD for the moment. So think about Y is equal to half x minus x bar. What does it do to you?
Half y.
What?
Half y transpose y.
So first term is nothing but, so you could have just seen from here. Because Q is PD, you can write Q as this, and this is nothing but square term, y transpose y. What happens to this?
Because like you have to get right transpose because like this Q, you get Q per half times. You don't need like a transpose in the Q's to like something.
It's okay for them. It will all work out. But this is completely okay. You can always write this. And you can take positive, definite, symmetric, whatever you want.
Okay.
Not a problem. So what happens to the first term? This is over here. So objective is y transpose y plus what? Sorry? You, this also exists because it's positive definite times okay. And what happens to the constraint? So now let's start talking in terms of constraints. Let's see transpose here. Yeah, it is there. So I could write it as and what happens to the constraint?
We can take the AX minus B, so we can take the pseudo inverse AX minus A transpose one.
Okay.
So we can take A outside and we get an expression X minus something is equal to 0.
See, now we've written objective function in terms of y. You have to give me the constraint in terms of y. That's all. Earlier constraint was Ax equal to B. And remember, x bar is also such that x bar is equal to B.
So then A times X minus X, A times Y is equal to B.
Constraint is?
AY equal to 0.
That doesn't sound right. Something is missing. You would need a q to the minus half y is equal to c. So that's what I give you the hint that a itself will get transformed because this is a new matrix. And what was my original form? X minus c whole square subject to some matrix times x equal to 0. So this is an equivalent matrix which I can write. Okay, so now what is my answer? Now that I have expressed this, what is my answer? Answer meaning the solution to x. You still have to complete the square. But completing the square, that's another thing you should notice. That's why I left it. Does it matter completing the square to the object, the optimal answer or not? Is everybody with me that what I've written as objective function is not in that form yet? It's not x minus c whole square. You'll have to do some completion of squares. But that doesn't affect the optimal values what my claim is. Because what is missing in that? Some constant term. The constant term is not going to affect my optimal answer. So just simply add it. So here there is no addition and subtraction by the same quantity. For free, you can just add the remaining term. It's not going to change. See, this is the, I think maybe doing this for the first time, so I'll do it formally. We're not adding and subtracting the same term. We're actually just adding something for free and claiming that the optimal answer doesn't change. Because all we're after is the optimal answer. The evaluation of the objective function at that answer might change. But that's a different story. All we're interested in finding the optimal answer.
Oh yeah, we can take Q to be we can take Q to be symmetric also in the sense that you had said actually it won't matter actually because
Q is fine to be
always
symmetric.
find that form to be of something like you can.
No, for technical reasons, you need it to be positive semi, at least positive semi.
Yeah. But we can take it to be symmetric.
All right. So again, let's write it as observation. Minimize f of x is equivalent to minimize f of x plus theta, where theta is a constant. This equality doesn't mean that the objective functions are equal at the optimal point. All it means is solving this problem is equivalent to solving this problem. Because once I get x star, I can just plug it there. So x stars are the same as what this equivalence is. So in here, if I just throw in the remaining term, which will make my square complete, which is nothing but let me just make sure that transposes are correct. C transpose q to the minus half C times 1 by. Now this will allow you to write it as y plus q to the minus half C 1 by 2. So now the new problem is a so in place of my original C, there is a, so C has become minus Q minus C and A has gone to AQ. So whatever answer you had earlier, just throw in this and that's your answer. Everybody with me? So that's that much for the convex function. So like last time we did this for convex function, for quasi-convex. So for convex function, what was the necessary sufficient condition? In the constraint set that del fx transpose has to be for all y in the constraint set. What would be the appropriate condition for quasi-convex? First of all, try to imagine how quasi-convex is different than convex. So give me a picture of a quasi-convex function which is not convex. Sorry. X cube, will it help you? No. We said this kind of function is also quasi-convex, right? Simplest definition was all the level sets are convex. Okay, now tell me what is going on very different compared to a convex function here. First of all, is a local optima a global optima? That's the first thing you should check. Yes, no? Yes, why? The picture itself is there. It can't be, right? This picture, can you point out to me a local minima which is not a global minima? No, so disregard this line. Let me erase that line. I claim that this picture is informative enough. That's why I didn't want to draw x cube. You don't even have to try and prove. You can just give me a picture and that will be a counter example.
Take that just to.
So you can call it the value, that thing as value, the first descent and the second ascent, if you want to name it.
When the first descent is restricted to the part of the first descent.
Yes,
There's a minimum over there,
correct.
but that's not the global minimum.
It's as simple as that. I can make it as flat as I like, and that will still remain quasi-convex. You can actually have a straight line, which clearly is a local minimum, right? But I have deep valley where the global minimum sits. So clearly the first condition itself is wrong, that the local minima is not going to be a global minimum. But what can we say something like this? Can we say something like this? That at the optimal point, what's going to happen? And what does it rule something out? This was necessary and sufficient. This example rules something out. So what I'm essentially asking is, look at the same condition, flip the inequality. Just say strictly less than equal to 0. Can you find an optimal point at which it is in fact less than equal to 0? That would tell us that necessity is out of the picture. Sorry, let me just write the task out. Can you construct a function for which del fx star x minus x star is less than 0, but still x star is local or global?
So this picture is there, right? We can take that. This
Give me, yeah, just tell me and I'll.
That's one point over there.
This one?
No, no, further up. Right.
This one?
No, not there, up there. Like, further up.
Here?
Yeah, somewhere there.
Okay.
And so now the slope over there is negative.
Okay.
But if you take y outside of it,
This-
so you can't take y outside. Because then you're restricting it. Yeah, so. From your local minimum. So
for convex functions, this is not possible. So what does it disprove?
yes.
If suppose this is true, I'll complete. If suppose this is true, what does it disprove? That this is not necessary. Is it sufficient is a different story. Okay. Sorry, you want to say something? We're still constructing. So is the task clear? What are we after?
Extra probably.
X star is a local or global minima. There exists an X, but still X star is local minima. So why was that not possible in a convex case? We proved it, right? If X star is local minima, this better be true. That's what we proved. What was the logic there?
The secant joining those two points always has to be above the time.
Did we use that?
Like pictorially, that's what.
Okay, then Victoria will tell me this need not work, if at all. You want to create something else, that's fine. By looking at this condition, what do you want to create? What has to happen? So let's say there is a point which is x star. Somehow that has to be a local min, correct? And what else has to happen to for this to work?
So you have a direction.
Yeah.
towards, so along the direction vector, you as you move,
Okay.
the function value will be here.
Mhm.
Will be higher, lower than the direction.
Okay. So something like this is what you're asking for.
Yes.
Okay. So for this x, what will happen? As I go along this direction, this a shallow valley here, and then you can take this to be, as long as it's quasi, so something very careful what I draw. You have to ensure that this is still quasi-concave or quasi-convex. Would that work if such a thing I could construct?
Probably the x star we're trying to take it as a local minimum. But
Yeah.
like if you take a point in the neighborhood, then if it's less than x star, then it's not. Then
No, but that's the whole point. It need not be very close to it, right? Why should it have to be so close? For any x, if I can demonstrate any x for which this is true, this is violated. This is true for all x. That's what we have proven. So even if I can produce one x in my domain for which that is violated, I'm good. So it doesn't necessarily have to sit inside that neighborhood.
Okay.
See, that's clearly not true because of the very fact that it's a local minimum. But the local minima need not be global minima, gives you all sorts of possibilities. So hopefully you will.
When you apply a global minima also, but we cannot get a global minima having that property.
If there are two global minimas, okay, let's just scratch it out for the moment. I have to think. Hopefully you will construct one. So the corresponding answer here turns out to be a sufficiency answer.
It's like a water slide.
So what you will get is for the quasi-convex case, and the proof is straightforward, that only a sufficiency condition. That is, if del f transpose x star y minus x star is strictly greater than 0. That also is important. For all y in x, then x star is 0. Say global minimum. Actually, you can say optimal. And directly follows from, I don't remember I gave it as homework or not. So there was an if and only if condition for quasi-convex functions. It follows from here. F is quasi-concave, I'm saying convex, if and only if f of y less than equal to f of x implies del fx transpose. Is it in the homework? Number 3 possibly, I don't remember. At least I did say something about it in the class. That much I remember. I didn't. So this will imply this condition. The proof is very similar. I'm not going to go over this. All right. So now lots of definitions for the rest of the class. You don't seem happy. What's going wrong? This condition. Okay, what are you thinking? Tell us also.
Thinking how it will work in the graph. So one thing, so the fact that we told that whenever there is a to have a minimum violating the condition but still less than zero, that along the trajectory, if you walk, the functional value will be less than the trajectory. So in the global case also, it will not be possible because if we want to hold that condition, then in the global minima also it will fall down. Like it will, yeah, the function has to decay
Okay.
basically.
Okay, let's not. Now, there's something interesting to note from here. This is strictly greater than zero. What does it imply? That the gradient at x star necessarily has to be. While here, that's not a requirement. This is where it really changes between convex and quasi-convex. Because I could essentially, over any domain, I can create a convex function whose minima is sitting inside at a point where the derivative is zero. This telling you that's not going to happen. But that's why it is only a sufficiency condition. It's not a necessary condition.
Because then you have a global minimum whose thing is actually, gradient is actually zero, so it's not a necessary.
Yeah. So, few points to note between convex and quasi-convex. You do end up looking at quasi-convex problem all the time. When you're outside of this course, you'll try to minimize some function which is not convex. It's quasi-convex. What do? We'll talk about it. If I know how to solve a convex problem, how do I know to solve a quasi-convex problem? We'll come to that in the class today. But do note these important differences between convex and quasi-convex. All right. So now prepare yourself for lots of definitions. This might be the only class where we'll do lots of definition. So definition. A generic optimization problem is minimize f of x subject to f. I don't like this notation, but because it is followed in the book, I would rather call it gi of x to avoid all the possible confusion. But the book does this, so I'll stick to it. It's g x. So this is for I going from 1 through m. Yeah. And j going from p. So this is called the objective function. These are called inequality constraints, and these are called equality constraints. And a standard convex OP is when f of x is convex, fi is convex, and the only equality constraints are allowed to be of the type ax, ai, aj, bj, j going from. So big step down. This is called a standard form. So what would be your immediate question? You should ask, right? You wrote a very generic program. Suddenly you came down to something much simpler. Why? Nobody has that question. I would have asked that question if somebody showed me this. This is quite restrictive, right? No? Okay, give me a problem which is not in the standard convex program. Give me an example of a program. So let's call the other thing just a program. Let's call this convex program. So give me an example of a program which is not convex program and which is still useful. That will convince you that what I'm writing is quite restrictive.
So F is not necessarily correct.
It's pretty clear what I mean. Give me a program which is not a convex program. But don't construct a contrived one. It should be as generic as it should be. And still it will not fit the convex program. But the whole world is captured by convex programs. Oh. So if the answer to that is no, then you should be able to give me a program which is not convex program. X as step function. So what? Wait, I said it should be useful, and I'm not asking for some random choices of functions. By program, I mean you want to solve some problem, right? Minimize f of x subject to some constraint. Give an example which is not convex, according to my definition of convex. It should not take so long.
Minimize the order of x given that x transpose x minus 2x.
Why so complicated? Does it have to be that complicated? You can just play with the equality constraint. X1 square plus x2 square is equal to 1. You can subtract it out. So you can call it h constraint as x1 square plus x2 square minus 1 is equal to 0. What does it mean? It's a circle. On the circle, you can try to minimize whatever you want to minimize. Now, it's as simple a problem doesn't fit. Is it not clear that this is too far too restrictive? But this is what we can solve. So that's what we will restrict ourselves to. Inequality, you can throw in any convex function you like. The equality is where the maximum damage is being done. The maximum restriction is coming on the equality constraint, because that is what is hard to control. If you put Hj to be arbitrary function, it's very difficult to control. So Hj is being replaced by simple affine constraints, that Ajf x equal to Bj. And that is where all the most of the restriction is. Any other example? So the example I gave was, think of minimizing. This is your domain. It's not even convex, just the perimeter of the circle. You can try to minimize whatever you want to minimize. That will fit here, but won't fit here. Okay, so that's that. So one example. So if I give you a problem of this type, minimize f of x, sometimes represented by f0 just to differentiate between the objective function and the constraints, subject to x belonging to upper bound and the lower bound. Is this in standard form? Standard convex form? No, it's not in standard convex. Why is it in standard convex form?
Say anything about
What?
the F naught.
No, f naught is fine. You can take f naught to be a convex. That's not a problem. But how have I written the convex constraints?
X equal to u and
So I'll have to, at least the way I'm writing, and this is just a nomenclature. There's nothing technical about it. How should I write it? The way I've defined it, it should be L minus x to be less than 0 That's correct, right? And x minus u to be less than 0. That's the form. I just want to impress upon you that this is what we want. Nothing non-trivial is happening between these two. This is a standard form. This is not a standard. That's all. So you might have to inflate the number of constraints in the way you write it. Here it was only one constraint. The way it is written in this form, it is more than one. Now equivalence. So take for example, the norm question you ask, minimize norm over equivalence Rn. Is this in standard form?
Yes, but we don't have it.
Constraint is okay, but is this function convex?
That the norm. Yeah, so the norm is called.
Or is convex? But why worry so much, right? I can transform this somehow, which will clearly convex. So what should I do? That's why I wrote equivalence. You could simply go to what is the equivalent problem that is clearly convex? Simply square it. Can the answer change? Here there is no doubt that this is convex. If at all there was a doubt there. So this is what, how you want to write this makes all the difference. Because eventually what happens, people have developed convex solvers. They would take only input as convex functions, or sorry, convex programs. How you input it is very important. And all the guarantees will be also given to you for a convex program. So if you want to have a guarantee for your problem, you will have to associate an equivalent problem which can be written in that form, which may or may not be obvious.
But why do you also need to check about the domains also, right?
Yeah, I kept the domain the same. I didn't change the domain. If I did, of course, I have to worry. That goes without saying. That if I'm changing the domain, of course, the answers will change. Not necessarily, but can. Another interesting way of doing things. So as I said, this is all either rewriting it or equivalent form. There's nothing technical going on today. So this is called what is known as slack variables. And all these techniques are very useful in going from one problem to the other. That's all there is. So what kind of constraints we had was fi of x to be less than or equal to 0. If you want to associate an alternate constant with equality, what is the possible way of doing it? For this constraint, which is less than or equal to 0, I want to write another constraint with equality. And you'll have to do something else later. What is possible? Add what? Okay. So let's call it as SI. What should I do? Okay. And then what should I do? That's clearly SI is positive. Okay. And give me a crisp two-word answer why they're the same. If my optimization problem was minimize f0 of x such that fi of x is less than or equal to 0. You're saying I can write this as minimize f0 of x fi of x plus si equal to 0 and si greater than 0. You have to convince me that they will result in the same answer, right? Here I will get an x comma s because now the minimization is also over s. But the pair you're going to get here, xi star, comma, si star, and x star here. What is the correspondence? Okay. What's the magic? The two words, all that you have to say. You did something, right? From here, how did you go here? That this hold, it's feasible only if there exists a feasible SI. That's all you have to say. So that's the new word, feasible. What does feasible mean? A point or solution is feasible if it satisfies all the constraints, really. Yep. You may ask, what have I done by going from here to here? All I've done is added an extra variable. So the problem should only become harder. But you'll find cases where this is easier compared to this. Something is not clear.
Adding constant like 1 by n.
Adding constants help when? This is not adding constants.
Yeah.
Yeah, so we looked at the example. We're adding a constant, we are able to write that problem as a simple x minus c whole square problem, for which I know an exact answer. But that's not true everywhere. I'm just thinking of an example where doing this helps us.
Linear program. Sometimes.
I don't have it, so we'll just keep going. Okay, so this is interesting. This actually comes to your rescue a lot of times. Writing in the epigraph form. So assume that there is no constraint. Okay, and you're just trying to minimize f of x. Can you give me an equivalent answer in terms of the epigraph? Remember, what was epigraph? Everybody remembers epigraph? Here is my convex function. This is my, so what are the set of vectors which lie here? So AP of f belongs to x comma t such that t is greater than or equal to f of x. So does it tell you something how to possibly rewrite this in terms of this epigraphs? So just pictorially tell me what is this min of f of x look like in this picture in terms of t's and f of x's. Don't tell me that derivative is 0. Look at this equality. Yeah, tell me. So just minimizing t while t remains inside the epigraph. Is that okay?
Sorry, can you repeat?
You tell me, suppose all I have given is this information about the epigraph. I want to solve this problem. How can you express it in terms of epigraph?
Express that in terms of epigram.
So I clearly know that this point is optimum, right? But that my intuition is coming from the derivative, etc. Can you just look at the epigraph, the very definition of it, and express that optimal answer in terms of something? All you need to use is the definition that if x comma t belongs to the epigraph, this is true.
So for every x belonging to epigram of L, x will also be greater than equals to that minimize.
I have no clue about x. All I have is inequality between t and f of x. It's clear what's going on? So suppose I'll write the following: minimize t such that t belongs to epi of f. What kind of program is this? Don't worry about convex, convex, convex. Is this equivalent to this or not? Why?
Because if we think of like f of f to be a set,
It is.
then essentially it is having more terms which are higher than f of x.
Say it properly. You want to conclude that this answer is the same as this answer. Is the meaning of this clear? One way to show that the optimal value here is the same as optimal value here, you show that less than or equal to in both directions. That's one way of showing it. If that helps you. Otherwise, just give me a conceptual answer. What does it mean to minimize t such that t belongs to epigraph of f? Can it be lower than this? Just argue.
No,
Why?
because t is always greater than equals to f.
Yes, so I'm trying to suppress t as much as possible. And given the fact that it belongs to f, I can never go below that particular f of x. So if I keep pushing, eventually I'll go and hit the max level where I can go, or the min level, sorry. And that is exactly what min of f is. So this is one way of writing your min of f of x. So in the generic form, what you do is, instead of writing min of f0 of x and fi of x less than equal to 0 and hj of x equal to 0, to transform this to minimize t. Now I don't want to write this. So what is the equivalent answer I'll write? T greater than f of x, which is fi of x minus t equal to 0 and keeping hg of x. This just t belong to epi of f exactly means that. So it belongs to epi of all of them, and then I'm trying to push as small a t as possible. So this comes to rescue for many problems. Again, for some reason they don't have example right here, which I can give you. But hopefully this is clear that what is going on. And by pushing t as small as I can while staying inside the epi, I'm doing nothing else but minimizing f of x. And because there are possibly more than one constraint here, I have to do it for all of them. I'll try to come up with examples of each of this kind. For some reason, it's not here. Okay, so list. So shall we move on? Yeah. Everything should be clear. There's no hurry in going anywhere, but things should be clear. Okay, so let's try to, again, another example of equivalence. So minimize. So f0 of x is x1 square plus x2 square. What are the constraints? Such that f1 of x is x1 divided by 1 plus x2 square less than equal to 0, and h1 x is equal to x1 plus x2 whole square equal to 0. Clearly, it's not in the standard convex form. But I claim you can write in an equivalent problem where it is. What can I write this as? Which will be in Ax equal to B form.
Equals to minus 6 or x1 plus x2.
Okay, that takes care of that. What about this one? X1 less than equal to 0. Why does it work?
Because x plus y above is
Positive. And f0x is allowed to be convex, which it is. So I'll keep this. So another example where seemingly non-convex problem is equivalent to a convex problem. So there is no such theorem to our disadvantage really, that I can do a classification. You write a problem, however complicated, that there exists or doesn't exist any convex program which is equivalent to it. If such a theorem existed, a lot of research would have been simplified, because half the work is, in many papers you'll find it, is to prove that this program is convex. People write 10-page proofs to prove that certain problems are convex. Because once you have convexity, as we learn later in the class, lots of sufficiency conditions come in for optimal points. So this typically is a hard problem. Case by case you have to do. There is no generic technique to go from one. to the other. Okay, so now let's look at as I've written here, min of f0 of x, fi of x to be less than 0, and aj of x equal to bj. If I want to get rid of this, can you transform this program where this constraint doesn't appear, but it's part of it? What is it enforcing? This constraint is enforcing something, right? That x should belong to what?
That plane.
Plane. Yeah, but something more. You know this. Ax equal to b implies what? Something about range space, null space, something.
X. So B belongs to the column space. So
B belongs to null space.
column space.
Column space. Okay, so then that's what I want to get rid of, essentially. So this is telling you to stick in a particular space, right? I should be able to take that off and just include it somehow in the X itself. How do I do that? What is this constraint telling me? That you lie in certain plane defined by A. It's essentially range space of A. So how can I eliminate this and just write min of something subject to just one constraint? And that will give me an equivalent answer.
Just subtract that.
Subtract from where? No, that's not.
Yeah, but not this.
That is same as keeping it here. What's the difference?
So we just did it on.
Is the task clear? What we are trying to do? We're trying to eliminate the equality constraint and somehow transform either f0 or x or whatever. Create a new variable that you're allowed to do.
And in the constraint, can we take it off, not product of vectors?
Could be whatever you want. The answer should be that ax equal to b should not be there. That's all.
And so we can take a normal unit vector of the plate, and we can ask for all those x's.
Write the problem for me. It should be in the standard form. That is all I ask. Okay, so consider an x0 such that ax0 is equal to b and a matrix F which is whose range space is the null space of A. Can you use f and x0?
Instead of f not of x, we can write f not of f inverse.
Inverse? Why inverse? F inverse, and
X.
how do I know that it's invertible? That's not going to work. Something much simpler works, right? Take x going to last. Let's not say this. Just think of minimize f0 of fz plus x0 subject to fi of think of this problem. What is its connection with the original problem? Now the minimization is over z. That's all.
We are still minimizing over x naught itself because x.
No, x naught is fixed now. X naught is some solution which satisfies ax equal to ax0 equal to b. So pick any x0 you like, such that ax0 is b. You plant it there. The minimization here is over z. Why are they equivalent?
F side lies in the null space.
Okay.
So in that case, A that H A times X z plus X naught will also still be B. So that constraint is already this being satisfied. And
This standard decomposition. No one is comfortable. Go to the basics. Suppose I can solve this. What will it mean for that problem? I'm going to get a z star. How should I be able to solve for x star?
Will be essentially equals to z.
Why? So if you're convinced, then there should be no problem. The whole point is to associate the two problems, right? So why are you convinced that fz star plus x0 first of all satisfies ax equal to b? That's the first thing you should check. Does it do it? That's all you really need to check.
because it lies in the null space. So AF z is
And thereafter it's free to choose whatever you want to choose. That's all. There is no difference between that and that. All I had to do was to make sure that the constraint is definitely satisfied. So if I solve an z star here, I can just go to fz star plus x naught and find an answer there. That satisfies my equality constraint. Once I do that, here is z is a free variable. Z is not constrained in any way. So the same thing is being essentially rewritten via the decomposition. That's all. So not everything is hard. Sometimes it's trivial. So okay, so let's do the final thing for the day. Maybe not the final thing. One more. Let's do this. For linear fractional sometimes people call it programming also. To minimize C transpose X plus P over P transpose X plus F. Okay, subject to let's just say AX equal to B and GX. So this is a squiggly, strictly dominating essentially. Each component here is smaller than H. Terrible notation. Let's just stick to this. Nothing will actually go wrong. Okay. Let's suppose you want to solve this problem. Clearly not in standard convex form. Right? What should I do? Or what can I do rather? And domain is where? So domain is X such that in addition to X equal to B, P transpose X plus F is greater than 0. The domain of F is this. So the actual domain is intersection of this and AX equal to B. The point is, can you write this in my standard convex form?
So if I want to make the denominator as a square,
Square.
multiplying this,
It's a scalar, right? So think of transformation. Let's call Y and Z, little z. And 1 over essentially basis vectors, you can think of it. So what's the objective function in this new basis? Minimize X, so C transpose Y plus simply Z. Sorry, D times Z. And what are my constraints? I've added a new constraint. So this will simply give you AY minus BZ equal to 0. See, the denominator will disappear because it's the same. AX equal to B, right? Do I need to throw in an additional constraint? This is also true. E transpose Y plus what times Z is 1? D times Z? Sorry, F. F transpose Z is 1. This is by construction. All you get is numerator, you get E transpose X plus F. And what other constraints I should throw in?
To bring in the domain, that's the question. Right?
It's greater than 0. Somehow strict is not required. Why?
You can't divide it.
Let's see whatever answer we get. Let's suppose this is my program. Point is it equivalent or not equivalent? If I solve this, what do I get back? Their variables are y and z. So we'll try to prove less than equal to in both directions. Which direction is easy? So here you're going to get a y comma z pair. Let's call this y star z star. Here it's only an x star. So given an x star, right? What should I do? I'll collect y and z from here. Will the objective function be equal? So maybe something is missing here. So suppose I want to minimize f of x subject to some constraints. Okay, phi of x less than equal to 0. You have another program g of x such that gi of x less than 0. What is sufficient to show that solving one is equivalent to the other? That let's say
Product. If I G, if G.
I don't know how you even thought about a product. Okay, suppose y is feasible, gives you a function, let's call it h, which gives you an x, where x is feasible here. And the same thing can be done in the reverse direction. For every x, I have a function, let's say m, which gives you a y. So x is feasible, y is feasible. If this is given to you, what can you conclude? Is it clear what am I saying here? Look at this program, find a y which is feasible here. I can create an x which is feasible here. And I can do the reverse process as well. What can you say about the two programs in terms of their equivalence? Let's not hurry this. Yeah. Is setting clear?
Y is feasible here, we can find x which is feasible there and vice versa. So there
Yes.
is, 1 to 1
What is the final claim do you want to make?
So the feasible set here and the feasible set here is 1 to 1, right?
Okay, so
So if you can find a solution, so the solution of this will be 1 to 1 the solution of that.
okay,
So and that so this,
say it completely.
so whatever solution we find over here, if we find that solution, whatever that solution is the same as the solution here with respect to that the functional transform would be.
Yes. No, but what about the program I'm trying to solve? I'm trying to solve this, right?
Yeah, so then it's equivalent. Because we found a 1 to 1 space corresponding between the feasible sets. And the solution is one of the feasible.
Yes.
And so we have a 1 to 1, like if the solution over here is linked to the solution over there, and that's the only two link, like that's the only
Yes.
link between these two.
Yes.
So then the two programs are equivalent because if we solve this, we solve that, and solve it. If we solve it.
Okay, so let's say this is my y space. This is my x space. Right? What am I saying? I can take one point feasible here, and I can go to a particular x. Similarly, I take a point here and I come to. What are you trying to say? This much is given to you. Now make the claim.
So then the solution is also one of the feasible.
So suppose I find y star. It corresponds to some point here.
Yeah, so let's call that x
Okay.
0 or something.
Fine.
And x, because x star over here, it should correspond to some value y 0.
Yes.
Okay, so to prove that x 0 is equal to x star and y 0.
Is the pockets of y.
Okay. So
So then x naught is equal to h of y star. So then if x naught is equal to h of y star, then we are minimizing f of h of y star. Such that fi of h of y star, h of y is so sorry, I'll say it here. So y f of h of y star is equal to x naught.
yes.
So okay, wait, how much is it? First, yeah, we should cover it.
Is that what you want to try? Okay.
So then h of
This much is okay. Now, given that I can go in this direction also, what can I do? But now, given this is a 1-1 function, and as long as this remains convex, see, it's a composition map, right? There's nothing else. So, composition of two convex functions, as long as the inner one was decreasing, increase. I don't remember which direction it was. The outer one had to satisfy some condition. Both needed to be convex, and outer one was non-decreasing, I think. Then this is a convex program. So then I can actually, in fact, solve it. So what does it mean? And equivalently, I'll get g of m of x, gi of m of x less than or equal to 0. These are two problems. What are they really? Identical. Why?
Not identical. Like kind of,
Okay, let's stop at this point. I'll let you think on this. This is important.